What are the basic principles of fluid mechanics? In today's fast-paced world, understanding the basic principles of fluid mechanics is more relevant than ever. With recent advancements in technology and engineering, many are curious about how fluids behave. Whether you are a student, a professional, or simply interested in engineering, this topic is trending. Let's break down the essentials of fluid mechanics that you need to know right now. Fluid mechanics is a branch of mechanical engineering focused on the behavior of fluids, which include both liquids and gases. One fundamental principle is the continuum assumption. This principle treats fluids as continuous media. It allows us to describe properties like velocity, pressure, and density at every point, ignoring the molecular level. Another key concept is Newtonian fluid behavior. For many fluids, shear stress is proportional to the velocity gradient. The constant of proportionality in this case is dynamic viscosity. This relationship explains how fluids resist deformation when subjected to shear forces. Next, we have conservation laws, which are vital in fluid mechanics. The conservation of mass, often expressed through the continuity equation, states that the mass entering a control volume equals the mass leaving it. This means mass is neither created nor destroyed. The conservation of momentum is represented by the Navier-Stokes equations. These equations describe how fluid motion results from a balance of forces, including pressure and viscous forces. The conservation of energy also plays a role, as energy changes in a fluid system occur due to work done by forces and heat transfer. Pressure and buoyancy are also important principles. Fluid pressure acts perpendicular to surfaces and increases with depth due to gravity. Buoyancy arises from pressure differences in a fluid, causing objects to experience an upward force equal to the weight of the displaced fluid. Bernoulli's principle is another essential concept. It states that in steady, incompressible, and frictionless flow, an increase in fluid velocity leads to a decrease in pressure. This principle is fundamental in fields like aerodynamics and hydraulics. Viscosity is a measure of a fluid's resistance to flow. Depending on viscosity and flow velocity, fluid motion can be classified as either laminar or turbulent. This classification is important for engineers when designing systems. Lastly, hydrostatics and hydrodynamics are two branches within fluid mechanics. Hydrostatics deals with fluids at rest and the forces they exert, while hydrodynamics studies fluids in motion, including flow patterns and forces acting on bodies. These principles form the foundation for analyzing and designing systems involving fluid flow. Understanding them allows engineers to predict fluid behavior and optimize system performance. As technology continues to advance, knowledge of fluid mechanics remains essential for innovation in various engineering applications.